Our topic, as you can see, is Journey to the Dark Side, Dark Matter and Dark Energy. Please welcome Dr. Robert Piccioni.
We are seeing some of the very first galaxies forming in this image. And from this image and many others, astronomers estimate that there are over 100 billion galaxies in the entire universe, each of which has an average of about 100 billion stars. So our universe contains this immense amount of material that we can see. But actually, that's just a drop in the bucket, because there is vastly more in the universe that we can't see. In fact, the vast majority of the universe is completely invisible, almost impossible to detect, and something that we know very, very little about. So let's talk about two of the greatest mysteries in our universe: dark matter and dark energy, which together account for 95% of all the energy in our universe. Now, one might well ask, if it's invisible, if it's almost impossible to detect, how do we know this stuff is there? And what is it like? What do we know and what we don't know? And what may we never know? Well, let's talk first about dark matter. Now, the third bit of evidence comes from something called gravitational lensing. And this is due to Einstein's theory of general relativity. And he made the very profound and surprising statement that matter can bend light by its gravity. So if we have a very distant galaxy, as the one on the right, the light from that very distant galaxy can be bent by any galaxy that happens to lie in between, and that finally reaches Earth as if the light had gone through some sort of lens. And all that depends on is the mass of the intervening galaxy. And it doesn't matter whether it's a galaxy we can see or some matter that we can't see. All that counts is how much matter is there. So using gravitational lensing, astronomers have found these very interesting looking arcs. You see this arc here in white? There is a very faint arc here in green, and there's an arc at the top there in red. And these are images of very distant galaxies which are being lensed by the mass of this large galaxy cluster that we see in the lower right. So the mass of that galaxy cluster is distorting and magnifying the images of what lies beyond. And we can compute the mass of this nearby cluster by looking at how much distortion there is in that light. What sort of a lens did it take to make this distorted image? And the picture that astronomers come to with respect to dark matter is that when we look at the light surrounding a galaxy and look at the distortion in that light, we can tell what the dark matter is around the galaxy that's holding all those stars together. And do you see that sort of fuzzy purple area there? That's where the dark matter is, according to a computer calculation based on the distortion of light that we see. We can't detect that stuff directly. It's dark, it emits no light. But what we can detect is how much it distorts the light behind it. And so the picture is that dark matter is surrounding all the existing galaxies. It's like a halo. Now, normal matter is capable of condensing to an enormous degree, by a factor of a trillion, to form things like stars. But dark matter doesn't seem to be able to do that because it can't radiate away its heat energy. So, the dark matter, we believe, because it's so much more massive than everything else, formed the initial structures of the universe. Wherever the dark matter started to coalesce, it created a well in the landscape of the cosmos. It dug a hole, a valley in the landscape. And the regular matter fell into the bottom of that valley and formed galaxies and stars and condensed to a very high degree because the normal matter can radiate away its energy. And so the dark matter, in fact, is responsible for the structure of our universe. This is a computer simulation of what our universe looks like on a very big scale. Each of these little white dots is actually a galaxy, not a star. And the universe is structured in these filaments, which intersect and form these larger clumps where we have super galaxy clusters. And all of this fine structure in our universe was created when the dark matter started to accumulate and create these valleys, these rifts, and these great depressions, these gravitational wells that the regular matter fell into. In fact, without dark matter, there wouldn't be today any galaxies or stars yet in our universe, maybe even not ever. So the dark matter had an essential role to play in the development of our universe. Now let's talk about dark energy. Dark energy was detected because it controls the expansion of the universe. No small detail. So let's talk about that expansion of the universe then. So the expansion rate of the universe dropped, and then stopped dropping, turned around, and started going up again. The expansion rate increased. So the expansion rate of the universe is actually accelerating. The universe is getting bigger, faster, and at an ever faster rate. Well, we have an idea why. This is what we call dark energy, and we have an idea why there might be dark energy. And it has to do with some very strange things from quantum mechanics, which are called virtual particles. Now, over the last 50 years, one of the most important things that physicists learned was that if we are going to understand everything about everything, we have to begin by understanding a lot more about nothing. We used to think empty space was, well, nothing. That was pretty simple, but wrong. In fact, empty space is a boiling cauldron of particles that flash into existence and disappear again, continuously, everywhere, all the time. There's no rest into empty space. It's a very complicated thing, nothing. The reason is that quantum mechanics recognizes that there is an inherent limitation in nature to how precisely and how quickly you can measure energy. And because of that limitation, which Heisenberg was absolutely certain about, and he enshrined in a principle called the uncertainty principle, it's possible for particles and antiparticles to spontaneously appear from nothing, exist for an instant, and I mean like a trillionth of a second, and disappear back into the nothing with no trace that they were ever there. They are indetectable because Heisenberg doesn't allow you to measure small things that fast, that precisely. So, in fact, really what's happening is these virtual particles are borrowing energy on a very short-term loan from the bank of Heisenberg. Now, you might think this is a physicist's bad dream. After all, since we can't detect them, how do we know they're there? Actually, this is one of the most firmly confirmed and accurately verified facts that any human being knows, the fact that these virtual particles really do exist, because they affect the properties of the particles that we do know, the stable particles. So, if we accept that fact, what are the consequences? Well, the space between galaxy clusters will continue to grow as the universe expands. But galaxy clusters themselves will not grow because they're held together by a stronger force, the force of their mutual gravity. And smaller structures will also not expand for the same reason. Galaxies will not grow, stars will not get bigger, planets will not get bigger, and people will not get bigger. At least not for cosmic reasons. So let me conclude by saying that dark matter, this strange substance that we really don't have any idea what it is 22% of the entire universe and about 6 times as much as all the regular matter that we know. And dark energy, which may be the virtual particles of empty space, is 73% of all the energy in the universe. And after 400 years of quantitative modern science, we have nailed down 4.5% of what's out there. somewhat discouraging, somewhat embarrassing. But the good news is that we leave it to the future generations of young scientists, many of whom I hope are in this room, to solve these great mysteries of our universe. But for all of us, let me say that you are never too young or too old to wonder why. Thank you very much.